Bueno, I have the pleasure to introduce David Lederman. He received his PhD from UC Santa Barbara around 1990, if I recall. I was there as a postdoc. So after he finished his PhD, he went to UCSD, San Diego, with Ivan Schuller. And after his PhD, his postdoc in San Diego, he won a place in West Virginia University, where he stayed for 20 years. Since 2015, he's been a professor in the physics department of UC Santa Cruz, and where he's also a director of material science and engineering initiative. His research interest spans areas of magnetism, magnetic materials in reduced dimensions, phase transitions, and bioelectronics. So I will say that also that he has extensive collaboration with many researchers around the world, and he has an outstanding career in physics. So welcome, David, to give us a talk about antiferromagnetic spintronics using model transition metals, metal fluorides, thin films. Thank you very much.
Okay, thank you, Carlos. And I think I owe my career in some sense to Carlos because he and I were at UC Santa Barbara at the same time, and I was a young graduate student starting out, and I did my PhD under basically his direction. So I want to thank him not only for inviting me to this talk, but also, you know, for mentoring me. And it's been over 30 years. I actually graduated officially in 1990, and but yeah, I basically owe my career to Carlos. So thank you, Carlos, and maybe one of these days I'll be able to be there in person. So anyway, today I'm going to talk to you about antiferromagnetic spintronics, specifically talking about model transition metal fluoride films. And by the way, if you have any questions, please feel free to interrupt, and I will do my best to answer your questions. The talk is kind of long, but so I'm not sure I'll be able to get through um, the entirety of it all. I'm going to start out with an introduction. I'm going to talk about what I would label as ancient spintronics, talking about exchange bias, but there is a very surprising, I think, aspect to it that's actually very, very recent. So that's why I wanted to talk about that. And then I'm going to talk about spin pumping in an antiferromagnets. And then if I have time, I will talk about magnetic coupling between topological insulators and insulating antiferromagnets. So we'll see how far we can get. And again, feel free to ask questions if you have them. So I want to start out by reminding I understand there's probably some students and maybe some non-experts here perhaps. So I just wanted to very briefly give you a brief introduction to magnetic materials so that we're all on the same page. And there's several important concepts that we have to remind ourselves for this talk. The first one is the phenomenon of exchange, which has to do with the fact that orbitals that of different atoms, when they overlap, there's an exchange interaction that can cause the unpaired spins to either align parallel to each other or anti-parallel to each other. It's a kind of a complicated issue to decide from first principles whether this exchange is, this term here, J, is positive or negative. And you can see that if J is positive, the way I've written here with the negative sign, then the minimum of the energy occurs when spins align parallel to each other, and it's when J is negative, then we say we have antiferromagnetic exchange, and these align anti-parallel to each other. So that's one important concept. Then there's the concept of anisotropy energy, and this one has to do with the fact that there's nearby atomic neighbors, and they can actually affect the way in which these once you have something that's magnetic, or even if it's not, doesn't have long range order, but these spins would like to point in a certain direction. So one example of this is an exchange energy that might look like this, for example, which is called a uniaxial anisotropy, where the z-axis has a special direction, and this is due again to crystal symmetry. It's not due to an external field or anything like that. So you can think of this as kind of like an internal field. And what would happen is if in spherical coordinates, sz squared goes as s squared cosine squared theta, classically speaking, we have a uniaxial anisotropy, and you can see that spins would like to point, in this case, along this direction, because if I plot the energy, this energy as a function of theta, right? There's there's a minima at 0, and then there's a minimum here at 180 degrees. And in the middle, then these things, they are they're in a high energy situation, so they don't like to point in this direction. Okay, so this applies to both ferromagnets and antiferromagnets. That's the other important thing. And then we have, of course, the Zeeman energy, which occurs when you have an external magnetic field, or actually even an internal magnetic field B, right? Then the spins would like to align along that field direction. We have the concept of magnetization, which is the sum of all of the magnetic dipoles that you have in the system, and as a result of this, you can have a ferromagnet, which is in a field that has a spontaneous magnetization, has long range order below a temperature called the Curie temperature, and the magnetization response usually has some hysteresis due to the magnetic anisotropy that we talked about. So, for example, if you apply an external magnetic field H to the right here, and everything's aligned in this direction, and then you reverse the magnetic field, it takes a little bit of a negative magnetic field to actually reverse these spins, assuming that you have an anisotropy direction, for example, along this direction. And this is what it would look like. And then if you want to reverse it and go in this direction, then you actually have to apply a positive field to get these guys to overcome the energy burden that I showed you before. Okay. Okay. So this is what we have for our ferromagnet. Now there are materials that have, as I said before, they might have an interaction that makes the spins that are somewhat localized around each atom to be aligned antiferromagnetically to each other. So that means that, for example, you could have one row of spins that point in this direction, another one that points in this direction. There's different arrangements that you can think of. But the point is that this, in principle, has a very small magnetization. At low temperatures, it's really small as the field goes to 0. And this thing, even though it doesn't have a very large, or actually ideally 0 magnetization, then you can still tell that there's some long range order, magnetic order in this material. Okay, so you can't really plot something like this with a hysteresis look at you do in a ferromagnet, which has a spontaneous magnetization, because the spontaneous magnetization here is 0, but there is order. Okay, so that's sort of what I wanted to say, just from a very brief outline of this. And now I want to turn to the phenomenon of exchange bias. Again, this is kind of ancient in the sense that this was studied very intensely in the 1980s and 1990s and maybe the early 2000s. So that, physics moves very fast. So ancient is, doesn't, uh, maybe maybe 20 years ago. Okay, 25 years ago. So the question is, let's say that now you have a ferromagnet like this. It's got a magnetization and you can reverse the magnetization. You have an antiferromagnet right next to it. And then the question is, what happens when to the response of this system, the magnetic response, when you apply a magnetic field? Okay, and the answer is the following. In many cases, what you see is something like this. Here's your hysteresis loop. But now look, the important thing is that the externally applied field is actually um, uh, over here at 0. And then you can see that the hysteresis loop has shifted away from the 0 external field line. So it's not like I showed you before, where it was kind of symmetric about h equal to 0. Here, the entire thing has shifted to the left. So it's as if you had an external field in one direction that you're not reversing at all. So everything gets moved to the left. And then the question is, why does this happen? Okay, so here you have the remanent magnetization, which is this right here. I'm just trying to also show you some terminology that I'm going to use. This is the coercivity of the loop, the width of the loop here of the hysteresis. And then importantly is the exchange bias, which is the shift of the entire loop away from h equal to 0. This is absent when you have a pure, ferromagnet, and it's due actually to the antiferromagnetic ferromagnetic exchange interaction right at the interface. So this is an interface effect on the exchange interaction right at the interface between the ferromagnet and the antiferromagnet. Acts like an external field that you cannot uh, reverse in principle. Okay, and you could always write it like this. You could write it as some ex, exchange interface exchange with F dot S here, like I showed you for the energy of the normal exchange interaction. This is called, of course, the Heisenberg uh, Hamiltonian. Okay, except the only thing that matters here is the interface. Okay, now I want to stress to you that this 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 effect, this exchange bias here, this shift here, actually has some very important technological applications, mostly in data storage technology. So, for example, if you know when you're talking about giant magnetoresistance, which has to do with the fact that the resistance of two ferromagnetic layers separated by an insulator or maybe or a non-magnetic metal, the resistance can change by a significant amount, in this case 80% in iron chromium, when this thing goes from being anti-parallel to parallel. Um, if you wanted to use this as some sort of sensor or as a data storage device, then what you want to do is you want to keep one of these layers from uh, reversing. And to do that, you can put a pinning antiferromagnet here, which would keep this thing from reversing, because now the entire loop is, has an additional bias, if you will. Okay, so this is actually used in magnetic hard drives, and it actually was a very important um, development in the development of what's called a spin valve. So this is called a spin valve, and it's used in read heads in hard drives like this. So this is an animation from the IBM website, and you can see that here. If you think of these as bits, one to the right would be a 1 and to the left would be a 0. As the read head moves along in the media, then the resistance goes up and down, and that's used to detect whether you have a 1 or a 0. Okay, so pinning this thing here is very important. And the question is, how do you do it? I already told you that it's using exchange bias. And um, and that's what I'm gonna talk about next, which is how does this work? I mean, I already mentioned to you that there's some sort of exchange interaction, but if you look at the details, it turns out that it's not so simple. So let's look at some of the details of this effect. Okay, so exchange bias was actually was discovered in 1956, around 1956, by Mikkel, John, and Bean, and this was discovered in cobalt, oxidized cobalt. So it was basically cobalt with some particles of cobalt oxide, oxidized cobalt, which was cobalt oxide is an antiferromagnet, and they discovered this effect. Okay, so the mechanism that they immediately realized, if it's just a simple exchange at the interface, it would look like this. This would be the exchange bias, the shift of the loop, and would have to do something. It would have to be equal to something like the exchange interaction divided by the, per unit area, right? And this is the area of a unit cell. This is the magnetization, and this would be the thickness of the film. And because it's an interface interaction, the thickness of the ferromagnetic film matters. Technically, if the film is very, very thick, the exchange bias will be less because it's less affected by the surface. And but there's several problems with this. So the first one is that this gives you kind of the wrong magnitude. If you just put in reasonable numbers for this, you would get a number that's maybe 100 times too large from the effect that's actually observed. And the other important uh, fact is that when you have a compensated surface, so imagine now that instead of having an antiferromagnet that looks like this, that where you have one sublattice to the right, one sublattice to the left, like this, and alternating like that, imagine that now you have both sublattices present at the surface. Okay, this is called a compensated surface, right? Because now you have both sublattices. There should be no net exchange, right? Because this one would have exactly the opposite exchange from this one, and the whole effect should cancel. Maybe you would have a wider coercivity, but this thing should cancel. And then the other thing that might happen is that you might have roughness. Now, we all know that there's no such thing as a perfect sample, and therefore uh, uh, every real sample has some sort of roughness associated with it. And any type of roughness would actually kill the effect, even if you had a uncompensated surface, right? Because you would go from this uh, exchange here, where these antiferromagnetic spins point to the right. If you have a step disorder, then you would alternate between right and left, and the net exchange here would actually be opposite, and it would cancel out. And so it was kind of weird because this, microscopically speaking, this really doesn't exist. And so the question is, why do we even see an exchange bias in the first place? And it's a non, it's an effect that's pretty easy to measure. You can have exchange biases of 1,000 Ørsted or so. So there were several models that have proposed over the years. There's a model in the 80s by Malozimov, where he came up with a model where you have a random exchange with the surface due to disorder, and so locally you would form domains where the net exchange would be non-zero, and locally the antiferromagnet would adjust to the ferromagnet structure as you cool down through the transition temperature of the antiferromagnet, so that you would end up having local exchange. And then after, at low temperatures, the antiferromagnet would freeze, and then you couldn't reverse it. Okay. And so this model predicted an exchange bias that's slightly different formula. It looks like it looks similar, except that now it scales inversely with the domain size in the antiferromagnet. These are domains that are formed in the antiferromagnet, and so this would decrease the effect to a reasonable, something that agrees with experiment. And then another model has to do with something like what's called like an exchange spring type of model, where when you reverse the ferromagnet and the antiferromagnet exchange at the surface is not satisfied, then what would happen is you would create some sort of domain wall. And there were different models. You could create a domain wall in the antiferromagnet, you could create a domain wall in the ferromagnet. And so in this case, it's kind of like a spring. It wants to go in one direction, and then as you go in the other direction, it kind of the spring kind of like releases its energy. And so this has to do the exchange bias when you calculate it using this model is goes as the square root of A times K. A is like the exchange. It's like the exchange interface exchange. It's basically the interface exchange divided by the lattice constant, and K again is the anisotropy. And this again gives you the correct order of magnitude. Of course, you still need some net exchange at the interface, and this doesn't deal with that, right? Whereas this model actually does. So maybe you could say maybe the model, maybe you need both, a combination of both models. So basically, we had these questions, which was, all of these exchange bias models require the presence of uncompensated magnetization at the interface between the ferromagnet and the ferromagnet, and the fact that, the anisotropy of the antiferromagnet matters a lot. The questions were, can we detect these uncompensated moments in the antiferromagnet, first of all, because you need to have some uncompensated moments in order to have a net exchange. And what is the role of the interface crystal structure? Okay, so those are some questions that we decided to address. And when I was a student at UCSB, I did my PhD on these types of materials, these transition metal difluorides, which are kind of really good model antiferromagnets, and a lot of work had been done in phase transitions and trying to discern different types of models. For example, the random exchange model, and looking at finite size scaling, which was the topic of my thesis, by making super lattices of these types of materials, looking at finite size scaling and looking at phase transitions in dissimilar in super lattices made up of dissimilar antiferromagnets. These are really nice because they're basically ideal antiferromagnets, especially manganese fluoride. If you look in many textbooks, when they talk about antiferromagnets, they actually plot the data from this compound. Okay, so the idea is, can we take an ideal antiferromagnet like manganese fluoride and try and figure out, something fundamental about the exchange bias, given that we understand this material from a fundamental point of view, and very well, instead of using a very complicated antiferromagnet where other things might, complicate the analysis. So that was the idea. And again, so I just want to very briefly go over what the properties of these materials are. Both, like if you have nickel fluoride and manganese fluoride, they're both insulating antiferromagnets. They have a rutile body-centered tetragonal crystal structure. And just for those of you that don't know, rutile is titanium, is a form of titanium dioxide. That's just the name of the crystal. And in titanium dioxide, you have titanium at the corners here, and then you have, these would be oxygen. For these materials, these are the transition metal, in this case, manganese or nickel. And these green spheres here are the fluorine atoms. Okay. And when you take manganese fluoride or iron fluoride, which is even more, has an even more, an even larger uniax, it has a huge uniaxial anisotropy along the c-axis. This is the c-axis in this direction. And they're considered classic icing antiferromagnets, which means that the spins like to point up or down. Okay, especially near the phase transition, people have used, have measured the critical exponent of this thing and of these materials, and it's well known that it behaves very closely to what theoretically you would have in an icing antiferromagnet. Okay, so for manganese fluoride, the Néel temperature, the ordering temperature is 66.5 Kelvin. It's tetragonal, so the A and the B axis have the same lattice constant. The C axis is a little bit smaller. And iron fluoride has the exact same crystal, has the same exact crystal structure. The lattice constants are a little bit different, but it has exactly the same magnetic structure. Okay? Now, nickel fluoride is interesting because it's a canted antiferromagnet. That means it actually an isotropy makes the spins want to lie in the AB plane like this, and then it has it can't, the antiferromagnet, instead of being the two spins being like this, they actually cant a little bit spontaneously, and so they have some other interesting properties that are relevant to fermions. Maybe you've had heard talks about this, but I'm not going to talk about that today. But here's the important thing. A lot of the samples that I'm going to show you were grown, uh, were synthesized, grown using MBE, with the surface of the film being the 110 surface. And that means that this is a compensated surface, right? This is shown here in this orange. That's the 110 surface, and you can see that you have both spins present at the surface, right? So this is a compensated surface, all right? So with nickel fluoride, you have the same kind of crystal structure. The lattice constants are a little bit different, but the important thing here is that these are ideal antiferromagnets where you can test all of these, models and all of these theories if you want. These are some details of how we do these things. We have an MBE system. It's got multiple chambers. We use the different chambers for different things. This is the chamber that we use for our fluorides. The fluorides, they evaporate when you heat them up. We do this. We can do this using electron beam evaporation or thermal evaporation. And in this case, the fluorine bond to the transition metal is extremely strong, and therefore the thing evaporates as a molecule. Okay, and so it's in some sense it's easier to grow than an oxide, where in the oxygen bond, for a transition metal oxide is relatively weak, and so you lose a lot of oxygen, so you have to add oxygen. Here you don't really need to do that. And we have another chamber here for growing other types of materials. Right now we're growing topological insulators, etc. And we have a transfer chamber where we can transfer between the chambers and grow heterostructures without cross-contaminating. So it's a really nice system. It took me like 12 years to build this thing, using different grants, etc. We have a room in the back here where we make devices. You can see the orange light here. We have a mask aligner and a spin coater and all these things, so we can make devices if we need to measure the magnetoelectronic properties. So in these experiments, what we do is we cool down our samples in a field through the phase transition of the antiferromagnet, and then you can measure the magnetization versus applied field, and we do have a squid magnetometer in our lab that we use for this. So again, the procedure is like this. You cool in a cooling field from above the transition temperature of the antiferromagnet. You measure M versus H. And remember that the conventional view is that, when you field cool it like this, you end up with a exchange interaction here with low temperatures. The antiferromagnet is fixed, at least for low fields, right? So I'm assuming the field isn't super large. So what happens is the antiferromagnet, because the net magnetization is zero, doesn't respond to the magnetic field very much, whereas the ferromagnet tries to respond because it's got a huge magnetic moment, and when it does so, it creates essentially, all of these bonds, all of these exchange interactions are frustrated, and that's what causes the exchange bias. Of course, this is a simple view, and there's a lot more details that need to be figured out because of the issues with real samples having a compensated surface and disorder. This is actual an actual data, some data from an iron fluoride antiferromagnet with I believe in this case it was iron on top, and or it might have been cobalt. I don't remember this one, but you can see that you get a very nice clean exchange bias. And then the question is, okay, why is it that you have these uncompensated moments when you have a compensated surface? And so that's sort of what I want to address. And one question was, we know, do we actually have these uncompensated moments in the antiferromagnet, or is it something else? And so an experiment that we did back, a long time ago now, and this is in, I think, 2006, I believe, we did some pretty comprehensive measurements to measure the magnetization of using magnetic dichroism and in X-ray absorption. And the way this works, it's a beautiful technique. Unfortunately, you do need a synchrotron. You need to have access to a synchrotron. So we had collaborators at Stanford and then at Berkeley, where they have their synchrotrons, and they were able to do this measurement. And so what happens is you take circularly polarized X-rays that you tune to the absorption edge, the L absorption edge of the transition metal. And then you measure with the right-handed and left-handed polarizations, and the asymmetry that you might see, something like this, for example, tells you that there is something that's ferromagnetic. Okay, for most metals that are not magnetic, the right-handed and left-handed polarization would actually have the same signal, and then you would say, oh, this is not magnetic. But iron, for example, would look like this. This is the L3 and the L2 edge, and then you can actually and then you can do element specific measurements, because, for example, you could tune it to the ferromagnet and the antiferromagnet, and if the ferromagnet, for example, is cobalt and the antiferromagnet is iron fluoride, for example, then you can actually measure the magnetic properties separately of both materials. So that's what we did here. In addition to the circular dichroism, you can also measure the linear dichroism. Okay? And the linear dichroism has to do with essentially it's the same thing, except you come in with instead of coming in with circularly polarized light, you come in with linearly polarized light, and the linear polarized light now is sensitive to whether you have antiferromagnetic domains and in which direction they are. And again, you can tune this to the absorption edge of the transition metal and only be sensitive to, the part of the sample that you care about. For example, this is nickel oxide. Nickel oxide is an antiferromagnet. I'm not going to talk about nickel oxide, but I just wanted to show you an example of another antiferromagnet, and this is the linear dichroism, right? And you can see that in one direction of polarization, you get this absorption, the other direction, you get this. And so you can tell that there's an asymmetry, and therefore you have some antiferromagnetic ordering. So what we did is we made a sample that looked like this. We had iron fluoride grown epitaxially of magnesium fluoride. Magnesium fluoride has the same crystal structure as iron fluoride. It's got the rutile crystal structure. So we were able to grow this epitaxially here. Then we put cobalt on top. This is the ferromagnet. This is the antiferromagnet. We kept it with palladium because we didn't want to oxidize the cobalt and create another antiferromagnet, which complicate things. And this was all done in situ so that we didn't have to, oxidize anything. The palladium just keeps this thing from oxidizing. And so this is the signal. This is the circular dichroism, and then you can see that at room temperature, right? You can see the hysteresis loop of the cobalt. This is the black curve here. But in addition to that, right, we were able to see that the iron from the iron fluoride had some response. I mean, small, but it's definitely measurable here. And then at low temperatures, you can see that this is at 15 Kelvin. This is after field cooling. You can actually see the exchange bias here, right? You can see how this loop from the circular dichroism in the cobalt has actually moved to the left, right? But in addition to that, you can see that there is a circular dichroism due to the iron, and that the entire thing is shifted downwards, in signal like that. So that means you have some pinned ferromagnetic moments in addition to unpinned ferromagnetic moments in the antiferromagnet itself. Okay. Now, the other thing you have to know about this thing is this technique is that it's extremely surface sensitive, because the escape depth, you're detecting electrons. You come in with X-rays and you detect electrons. The escape depth of the electrons is like just a few nanometers. Okay, so we're only probing down to probably just this interface, not much more than that. Okay, so this is all coming basically from the interface for the iron sim. So at room temperature, we have free uncompensated moments that follow the ferromagnet, and at low temperatures, we have additional pinned uncompensated moments oriented anti-parallel to the easy direction. Okay, and that's because it's negative, shifted downwards negative. Okay. So this is kind of an interesting set of data, and you can see it here that you can see here that in green here we have the linear dichroism due to the iron in the iron fluoride. You can see that this tracks really well the transition of the antiferromagnet. Here it goes to 0 at the Néel temperature, which is, for these films, it's a little bit above 80 Kelvin, and then it stays 0 here. And then you have the circular dichroism of the iron, and you can see that this persists up to room temperature. And then in addition to that, you have this thing which is the shift, right? Those are those pin moments, and you can see the pin moments actually disappear at the same point at which the iron fluoride orders, right? And this is kind of like a measure of the exchange bias. Okay, and so again, this is the exchange bias measured from the circular dichroism, and this is the coercivity. And you can see that you can actually see even a peak in the coercivity. And this is something that you can actually measure just using regular magnetometry. So this was not a surprise, but it serves to prove that we were measuring the right thing. And this, by the way, this is the reference if you're interested in looking up this paper. Okay, this is from 2006. Okay, so this is the picture that we came up with, that we have the longitudinal the linear dichroism shows that we have long range order. It vanishes at the Néel temperature. We have interfacial magnetic order at room temperature. Okay, from the iron. So there's like a layer in here of the iron that's kind of ordering, that's tracking this thing. But then at low temperatures, this thing kind of freezes a little bit, and the whole thing shifts downwards when you look at the hysteresis loop. There was some other work done using X-ray in and X-ray in, X-ray out technique, which you can look up in a PRL by Sujay Roy and others that appeared at about the same time as our PRL appeared. Okay. Now, here's and there's another thing I wanted to tell you about this, which is very, very interesting as well. This was work actually a much earlier work because I want to convince you that this is actually an interfacial effect. And you know, at the time I was still interested in phase transitions and so forth. And this is basically the exchange bias, the shift in this entire curve as a function of temperature. And we measured this shift very close to the phase transition temperature. And you can see that, and I was able to fit this thing to a rounded power law. Okay, the details are actually in this paper. You can look it up. You can see that this actually solid curve here is not, it is actually a fit to a rounded transition that looks like this. And the critical exponent actually agrees more with a surface phase transition than it does with a bulk phase transition. So this kind of like drives the entire idea that this is dominated by an interface exchange effect. Okay. And now I want to talk very briefly about why is there such a strong exchange bias when the surface is nominally compensated, right? Because, right, this is the surface here. You can see both spins are on the same surface. And so the question is, why do you see this at all? Okay? And so I want you to consider this. This is a very recent idea that has just come out uh, about what are called altermagnets. And in this case, uh, you can look at the you can look at the people have been focusing on the band structure of materials of antiferromagnets that have a local symmetry where both, like if you have, for example, an antiferromagnet like this could be iron fluoride, right? You have the spins at the center are spin down, the ones at the corners are spin up. So this could be manganese fluoride or iron fluoride. But what you can see, and you could see it also in here, but um, I think this drives it a little bit more clearly, is that the local symmetry, right, with these octahedra, these are distorted octahedra made up of fluorine ions around the transition metal. It's different, right? You can see here this one, the apical ions, which is this one and this one, point in are in the 110 plane for this one, but in for this atoms here, right? They actually they're rotated by 90 degrees, right? So when you do a 90-degree rotation about the z-axis, right, you don't get the same local symmetry. And the point by Jairo Sinova and others who have been working on this, and Thomas Youngwirth, is that this creates, they make very interesting predictions about, for example, if you have an antiferromagnet that's conducting, that it would have just very interesting transport properties. In fact, you could get a polarized uh, uh, current, spin polarized current in an antiferromagnet, even though the antiferromagnet does not have a net magnetization. And I think this applies to the exchange bias too, simply because, you know, one sublattice has a different symmetry than the other, and the exchange with the ferromagnet that would be on the surface here would be affected by the presence of these fluorines in a different configuration from one sublattice, right? The spin down sublattice versus the spin up sublattice like this. And in fact, people have calculated the 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 um, the band structure. I think in Sinova and others have calculated the band structure, taking this into account. And you can see that along certain directions in the crystal structure, right? This is like spin up and spin down, like along this direction, right? You can see splitting, spin up and spin down. The red would be spin up and and blue spin down. And here you have to look at the dotted lines. It's not in every direction. And in fact, if you average everywhere, right, there is no net, polarized spin current. Like in a ferromagnet, of course, you have that in all directions, but in an antiferromagnet, you only have it along certain directions, and they've made certain predictions about the transport, and people are very interested in studying this material. There's actually a conducting antiferromagnet, a metallic antiferromagnet, ruthenium dioxide, which has also this same crystal, the rutile crystal structure, and there's a lot of interest in this right now. So this is the idea of altermagnets, and I think this idea of altermagnetism not only affects the band structure, but also the super exchange or the exchange interactions at interfaces. And I think you can explain a lot of this because what ends up happening is that this interaction at the interface would be robust against step disorder. Because if you have step disorder, like you lose like a layer of atoms here, the one sublattice always has the same symmetry, right, regardless of the disorder. And so this might make exchange vase really robust against disorder. And maybe that's why we observe this thing. I think this is very, it's fascinating that there's kind of like this view of uh, of this altermagnetism can apply not just to the transport but to magnetic properties of heterostructures. Okay, so anyway, if there are no questions about this, I will switch gears and I will talk to you about something else. I think I'm only going to get through this topic, which is the spin pumping detected electrically in insulating antiferromagnets. So this is more recent work within the last 4 or 5 years. So I'm going to tell you a little bit about how you can get electrical signals out of uh, magnetic excitations in insulating antiferromagnets. Okay, so this is interesting. People are very interested in what are called antiferromagnetic spintronics, because the goal here is to use electric fields to transfer information at very high rates, terahertz rates, with low power. Okay, so that's why people are interested in these types of spintronics. When you use a ferromagnet, the characteristic frequencies are usually in the gigahertz. So this would give you 1,000 times increase in speed. And just as a reminder, spintronics consists of transmitting information using the spin of the electrons. Ideally, you want to avoid, having charge currents, right? Because that's the thing that where you get most of the dissipation of energy. And so if you want to make something that's like a low power electronic device, then what you want to do is you want to have a pure, say, spin current, right? Where you have like some sort of magnetic signal that travels, and then you can, but you still have the problem that you have to somehow get an electronic signal out of that, an electrical signal, because that's how we use electronics, right? So people have thought about using antiferromagnets. They have magnetic order, as we discussed, long range order. They have no net magnetization and have been proposed for all kinds of applications here. This is from, in fact, a website at UC Riverside, um, where different types of applications have been looked at, or, even terahertz imaging, because terahertz on frequencies can actually penetrate biological tissue. There's other interesting applications. Okay, so let's talk about these antiferromagnetic excitations, which we want to use to transmit information with. Spins are not static usually. In fact, you have in an antiferromagnet, you usually have some resonance modes. And what happens is, even in zero applied external field, you have modes where you can get precession about an axis, and this is due to the internal fields, and especially the anisotropy and the exchange field. Okay, so you can have, in fact, for an antiferromagnet, an Ising antiferromagnet, like you would consider something like it's not exactly Ising, but an antiferromagnet with a strong uniaxial anisotropy, right? Like iron fluoride or manganese fluoride. You actually have two degenerate modes. That means they have the same energy, and they look like this. One of them actually has this one processing in this direction, will be counterclockwise, and then this one processes in the opposite direction. So they have opposite chiralities. Okay, and so the question is, can we somehow get these excitations and control them with electric fields? And the way to do this, most of the schemes that people have come up with to kind of do some transcription, transduce these magnetic excitations into electrical voltages, have to do with spin-dependent Hall effects. For example, the anomalous, the spin Hall effect or the inverse spin Hall effect, okay, which occurs even in non-magnetic materials or even in antiferromagnetic. Well, I'll show you. No, this is not. You don't need a magnetic material, and then you have the anomalous Hall effect, where you need a magnetic material. In the anomalous Hall effect, what you do is you have a magnetic material, and you run a current, and then you have a Hall voltage that is created like this. Okay, and that's and the reason this occurs, right? Even if you don't have even a zero field, right, is because um, you have an imbalance of spins in the conducting ferromagnet, and so you end up with more accumulation. You get asymmetric scattering due to spin orbit coupling, due to spin up and spin down electrons scattered differently, but because you have an imbalance of them in a ferromagnet, then you end up with a signal like this. Okay. Then you also have kind of related to that is the spin Hall effect, where in this case, let's say the material is not magnetic. What happens? Well, what happens is you would get equal number of spin up, say, and spin downs on both sides. You would not detect an electrical signal. But if you had some way of detecting this thing with the spin, if you were only sensitive to the spin, you would actually be able to see that. And people have done this experiment, and they have used the magneto-optic Kerr effect, for example, and you can actually see this effect, the spin Hall effect. Okay, and then you can actually have the inverse spin Hall effect, which is if you run a spin current like this, which could consist of like having spin ups going this way and then spin downs going this way. And when that happens, it's kind of like the inverse of this. And in that case, you end up with a voltage in this direction when you run like as polarized current going in this direction and this direction with opposite spins. There is no net current, right? So it's a net spin current, but you would get a voltage like that. Okay. So these are three important effects, right? And in this case, the spin current in this case is the electric field is perpendicular to the spin current and the magnetization. So you can see the spin current points to the right, you end up with a voltage like this, right? That's perpendicular to both the magnetization, sigma, and or the spins, sigma, and the spin current. Okay. And then there's the concept of spin pumping, which is another key issue that we need to talk about. And what this does is it creates a direct spin injection via charge currents. Okay, but how do you do it? Well, you could think about taking a ferromagnet, like here on the left, right, and running a charge current. And then what happens is the magnetization will penetrate into the non-magnetic metal, but it's very inefficient. Uh, First of all, because it requires a charge current, so in terms of energy, it's inefficient. But also, what happens is the magnetization decays as it goes into the non-magnetic material, right? And so it has a finite length here, so it's inefficient. Turns out that there's a better way to do this, which is called spin pumping. And what you do is you actually apply an external field or an AC field. For example, for a ferromagnet, it would be a microwave, and then you get these spins to start processing about the applied field like this, and then right at the interface, you have an interface between a ferromagnet and a non-magnetic material. This causes a spin current because as this thing starts processing, the procession actually decays as it goes in. But in order to do that, it needs to conserve angular momentum, and so it creates a spin current that flows in this direction. Okay, so that's a much more efficient way of doing this. And then if you have something that's like a strong spin orbit coupling, as it turns out, the spin current can be quite strong. Okay, the spin current, the spin pump current looks like this. It goes as M cross dMdt. And again, dMdt is involved because it has to do with the fact that this thing at the interface, it acts like a dissipation force. It tries to kind of stop the precession simply because at the interface, there's no more, magnetic material, right? So the exchange at the interface is different and you get dissipation of the, you get dissipation of the precession. Then the question is, can such an effect be observed in an antiferromagnet? Okay, you might think that's not possible because an antiferromagnet has no net magnetization, right? But I told you that there actually an antiferromagnet does have resonance modes. And so the question is, how can you control these modes using electric fields? So what you would do is you would inject a spin current, mostly dependent on what's called the Néel vector. The Néel vector is M1 minus M2. So if you take the sublattice magnetization will be this red vector M1 minus M2. And you notice they almost point in the opposite direction. So this is L. This is not angular momentum, by the way. Okay, so this is not L here is what's called the Néel vectors, M1 minus M2, which I've drawn here for this case, and I've drawn it out here for this case. So they're slightly different for the two modes. And then it turns out that the spin current that you can generate in this thing goes as L cross dLdt, because again, if you have an interface and this thing is processing and it encounters an interface, then it's going to look a lot like it does for a ferromagnet. Except now it's the Néel vector that matters. So you use the spin Hall effect. You can run a charge current through a heavy metal with heavy nuclei like platinum. You can generate a spin current perpendicular to the interface due to spin accumulation, and then you use the inverse spin Hall effect for detection. So it looks something like this. Okay, so this would be a device where you could you could create magnons. You could get magnetic excitations going from right to left here by running a current through here, because you get spin accumulation here due to the spin Hall effect in the platinum. Remember, the spin Hall effect doesn't require you to have anything magnetic. It just has to have relatively strong spin orbit coupling. This creates a spin current going downwards. This creates excitations in the antiferromagnet. The excitations travel to the left, and then the inverse spin Hall effect, when these things are processing right at the interface, creates a voltage that you can detect in the opposite way. Okay, so this would be a completely spintronic type device because the information is carried through an antiferromagnet, which ideally is actually completely insulating. So there's no charge current going from here to here. You're running a current here, detecting a voltage here. So I want to show you what we did to prove that this is possible. We did some work in collaboration with the National High Magnetic Field Lab in Tallahassee, Florida, where they have a tunable microwave source, well, high frequency microwave. So it's almost in the terahertz range. It's several hundred gigahertz. Okay, and so basically the experiment, I'll show you that the data confirm that we are coupling between the platinum layer and the antiferromagnetic mode. So I'm going to show you that this spin pumping mechanism actually works. Okay, so this is the film. This is what the sample looked like. We started out with a single crystal, and then the key here is having a very, very clean interface, because you want to be able to have a good interface between the non-magnetic heavy metal film and the antiferromagnet. So we grew another layer using MBE, right, to get a clean interface, and then we grew the platinum on top. And the idea is we could not, with a single crystal, is that we could not only do the spin Hall effect, but we could also do a resonance experiment and make sure that we are actually, by measuring the absorption, that we're actually hitting the resonance of the antiferromagnet like we're supposed to. Here, this is a read image of the film. You can see it's, very nice, very streaky, and anyway, I've showed you this before. These are some photos of the sample. Okay, and here's kind of like the idea of the experiment. You have the manganese fluoride. We apply a magnetic field like this. Okay, and then you should have a spin current flowing in this direction, and then that should create a voltage like this due to the spin, the inverse spin Hall effect. And so we tried different frequencies. These lines here are the resonant frequencies for the different modes. Okay, we tried 120, 240, up to 395 gigahertz. And anytime this red line intersects one of these lines like this, these are the two modes that are degenerate at zero field. If you apply a field, you break the degeneracy, the two modes, one of the modes increases in frequency, one decreases in frequency, and every time it crosses this, then you should see a resonance, and then you should see a DC voltage in your platinum. So it's like you're pumping in high frequency microwaves, and you should see a DC voltage. Okay, so this is kind of like the data right here. The red here is the resonance frequency of the antiferromagnet, the manganese fluoride. The black signal here is the inverse spin Hall effect voltage, right? And you can see that it coincides really well, which is what you want. And the other thing that's nice that was done at the lab is that you could actually do right-handed and left-handed polarized microwaves, and then you could select actually each of the different you could make sure that you're selecting the correct mode. So we looked at different modes. We have up here you have what's called a spin flop mode. I don't have a lot of time to talk about it, but I'll show you. There's a field at which the critical field where everything turns 90 degrees. That's called the spin flop mode. So we looked at this mode. This is mode number 1 here. This is mode number 2 here as a function of field. Looks like this. Mode number 3 looks like this. These are all modes that we were able to detect. And mode number 4 over here. So this is the resonance frequency as a function of field. These are the signals that we were able to see, and you can see that we were able to detect them with left and right circularly polarized lights, and you can see that the effect, the inverse spin Hall effect, changed from positive to negative field. That breaks the chirality of the radiation, breaks time inversion symmetry, and so in this case, when you have left-handed polarized light exciting these modes, you see it on the negative side of the field, and here you see it on the right, on the positive side of the field. So that's exactly what you would expect, and this is for this other mode, and you saw the exact same opposite. Okay, so this was very exciting for us. Okay. Okay, so it looks like I've run out of time, and I'm not going to talk about this. It was very ambitious. So these are my conclusions. I think antiferromagnets are promising for new technological applications. Even though these antiferromagnets have a low transition temperature, the applications, you could find maybe materials that have a higher transition temperature, or even now, there's a lot of interest in cryogenic electronics for quantum computing and other low temperature applications. Okay. I want to thank the team. I've done a lot of work at West Virginia University, where I was there for 20 years before I moved to Santa Cruz. These are my current collaborators, and my 2 students, and my collaborators at Stanford and Lawrence Berkeley Lab. And I want to thank you for your attention.
Muchas gracias, David.
Thank you, David. Sí, It's a very didactic talk. I would like to open the session to questions. I do have a few questions, but if anyone wants to start, probably Carlos has also a question. If not, I can start. In the spin pumping measurement, how do you control the angle? So in your high magnetic field facilities, can you rotate your electromagnet or something like that?
No, no, you can't. So that's actually very, very tricky, you know. I mean, it's like you have to be within like a couple of degrees,
Mhm.
and it was really, really hard. You just have to mount the sample really, really, because it's like essentially in a waveguide, and so you have to mount it correctly, and so you can see that, like for example, here I didn't talk about this, but um we our data shows that we were not aligned perfectly with it with this, and so we you to analyze the data we have to take into account that the modes do not look like the black line, which is when it's perfectly aligned with the field is perfectly aligned with the c-axis, but it was actually misoriented by about 3 degrees. And we actually had to do this experiment several times because initially our samples were so misaligned that the sample would torque, you know, because it's a bulk crystal. The fields are very
Mm.
big, and it would just kind of like come unglued and fall off the sample holder, you know. So we don't have a way to, in this case, to change the angle of the field.
I see. How thick is your platinum layer?
What? I'm sorry.
Thick is your platinum layer?
Yeah. What about the platinum layer?
The thickness of the platinum layer.
Oh, the thickness. I'm sorry. Yeah, I think I showed it over. I think oh, maybe I didn't show it. I think it was very thin. It was like maybe 5 nanometers,
Okay.
or
Okay.
three to 5 nanometers. Yeah.
And I have an additional question. Why your inverse pinhole effect signal does not follow your EPR signal? So I was expecting I don't know the similar shape of your IC signal, because if you see that, or if you take a
Yeah.
closer look of your EPR signal,
Yeah.
one could say that the resonance is I don't know, around 4.5 Tesla and 5.2 Tesla, according to the EPR, but in the
Yeah.
inverse pinhole effect signal is around 4.7. Is that reasoning correct?
Yeah, but I'm not sure. I can't remember if this EPR is more like a derivative of the signal, you know? So it's not like, I think the center of the signal is right here.
Okay.
You know, it should look like a derivative of a Gaussian or Lorentzian or whatever.
Yeah, yeah, yeah.
But I'm not sure. I mean, that's a good question.
Yeah,
Okay.
well, very interesting that you see signal in platinum having, I mean, voltage having just an insulator. I mean,
Yeah.
the whole issue effect is just surprising. Uh, it's, I wanted to ask you something about a long time ago. I hear talk by Miguel Kiwi from Chile that he said the exchange is actually coupling perpendicular to the antiferromagnetic direction. Is that anything to do with that?
You know, I mean, yeah, I mean, Miguel had this, there was this other theorist I can't remember, but there was this thing about coupling perpendicular to the exchange because of disorder, you know.
Yeah, because
So disorder would kind of cause, you know, some sort of frustration. So the thing, instead of coupling perpendicular, I mean, parallel to the thing, it
Parallel
would
to
actually
that.
end up, yeah, and it's due to frustration, but we have never, honestly, experimentally, we have never been able to see that, and
Okay.
the circular dichroism experiments that we did showed that in for us, it seemed like it's definitely parallel,
Okay. Thank you very
So,
much.
and so, and back then, this idea of outer magnetism wasn't so clear. I mean,
Mm,
I remember talking to Eric Fullerton and others about this, and we knew that the symmetry of the two sites was different, and we sort of, we had a kind of like a sense, maybe a qualitative sense of that, but now that
mhm.
this thing with outer magnetism has come out very strongly, I think now there's a stronger theoretical framework. And I think
Okay.
maybe that's the answer. Yeah.
The answer for the rutile structure. Okay. Well, thank
Hmm.
you very much, David, for the introduction. I think it was more for students, but thank you. And I see that you have done much more than you show. And well, thank you again. Hope to see you sometime in the south.
Yeah, I would love maybe one of these days I'll go down there and visit you. I would love to. And you're more than welcome to come visit us. We have a new material science. We're starting a new material science PhD program here. So we've graduated from an initiative to a PhD program. So if there are students that are interested in participating, we'll probably have next year we'll probably be admitting. Well, we'll be admitting students this fall, in case anybody's interested.
For the young people. Good.
Yes.
Well,
Good.
for me, I don't know if there's any other question.
Okay, so thank you everyone for being here and see you in 15 days. Thank you, David, again for your talk.
Thank you, David.
Thank you. Thank you, everyone. Bye.
Un abrazo.
Bye bye.
Igualmente, saludos, nos vemos.
Chao. Adiós.